In this video, we're going to show you how to perform hypothesis testing for population means and population proportions. We're going to use a number of examples to demonstrate that. So let's get started. The first example is for hypothesis testing for population means when population standard deviation sigma is known. Here's an example. A simple random sample of 50 items is taken from an inventory, and the average unit cost on the items is $25.50. The population standard deviation sigma is known to be 4. Because of this statement, we now know that this is a situation where population standard deviation is known and given to us. Test the hypothesis that the population mean is less than $26.60 using a 0.05 level of significance. So in this particular example, we have a sample, and from the sample, we know that the sample size is 50. The sample mean is 25.5, and sigma, the population standard deviation, is known to be 4. And we want to see whether the population mean is less than $26.60 based on that information given at a level of 0.05. So how do we go about doing it? Well, we're going to follow the standard steps in hypothesis testing. Typically in hypothesis testing, we have the 5 steps as follows. The first step is to set the null and alternative hypothesis. The second step is to set the level of significance. The third and the fourth step is to set the decision rule as well as the summary of the data that we can calculate. We call it test statistics. And based on step number 3 and 4, we can then draw a conclusion. So in this particular example, because of the fact that sigma, the population standard deviation is given, we're going to use this formula. Is that equal to x bar minus mu 0 over sigma over square root n. And we can use 2 different approaches to do the testing. The first approach is called the p-value approach, and the second approach is called the critical value approach, and we're going to do both. So the first thing we want to do is use the p-value approach to perform this hypothesis test. So let's get started. So first thing we need to do is to set the null and alternative hypothesis. So let's define what the parameter is when we do this problem. The parameter, of course, is the average mean cost, right? So we call it mu. You can either use mu, or you can actually use the mathematical symbol. And if you use the mathematical symbol, it would be mu, right? And we're going to use mu just to make it easy. And this is the mean cost. And what we want to do is to see in this particular example whether the mean cost is less than 26.6. So how do we set the hypothesis? We first set the alternative hypothesis. The alternative hypothesis says mu is less than 26.6. So we actually do the alternate hypothesis, which is called the research hypothesis first. And once we set the alternate hypothesis, the null hypothesis is just the opposite. And the null hypothesis is called x0. So x0 is the mu is the opposite of less than 26, so it is bigger than or equal to 26.6. Some textbook or some author, we would just use mu is equal to 26.6 as the null hypothesis. We can prove mathematically they are actually equivalent to what we're doing here. Okay, so that's the null and alternate hypothesis. Let me just format this a little bit better. And we can just format this better. And once we set the hypothesis, then we can now do the level significance. But before we do that, let's make sure that we introduce the terminology. If the alternate hypothesis is less than, we call this a lower tail test. So this is a lower tail test, and we will tell you later on why this is useful. Now, the second step is to set the level significance. In this case, the level significance is given to us, and usually we use the notation alpha, and or we can just type this up, right? So alpha in this case is equal to 0.05, so this is nothing to it because usually alpha is given to you in a question. The third step is the decision rule. This is how we're going to make decision. In hypothesis testing, the decision rule is also called the rejection rule. For the p-value approach, the decision rule is always the same. As you can see that if you use the p-value approach, regardless of whether it's a lower tail test, upper tail test, or any statistical test for that matter, the decision rule is always reject x0 if the p-value is less than or equal to alpha, or we can just say if p-value is less than alpha, it does not really matter. So we say reject x0 if the p-value is less than alpha. Alpha is equal to 0.05 as we defined in step number 2. So the question is, what is P0? Well, P0 is a summary of the data which would be calculated using the test statistics in step number 4. So in step number 4, we would calculate the test statistics and use the test statistic to determine the p-value. So step number 4 then is to calculate the test statistics. For this particular problem, in terms of testing for population mean, when the population standard deviation sigma is known, the formula, the test statistics for that is this. We compare what we see from the data x bar minus what we want to test, mu0. Mu0 is what is in the hypothesis. And then we standardize it by a standard deviation, sigma over square root n, and we use it as the test statistics. We can prove mathematically that if the null hypothesis is true, then this Z has a normal distribution, and we can then use the normal table, right? So compare what we see with what we want to test and standardize it so that we can come up with the test statistics. So in our case, let's write down what we know, right? So x bar is equal to, from the data, is 25.5. Right, sigma is given to us, so I'm going to just spell out sigma instead of using the notation, is equal to 4. N is the sample size, which in this case is 50. Right, so N is 50, x bar is 25.5, sigma is equal to 4, and mu0 is equal to 26.6. So mu0 is what is that we're trying to test in the null and alternate hypothesis. So we now know the 4 quantities. That means we know every quantity is in the formula. All we have to do is put it in. Right? So we say Z is equal to 25.5. This is what we see from the data. And what we want to test is 26.6. And then taking into account the variability, which is 4 divided by square root of n. N is 50. And that's how we should calculate the formula, right? And we can just use Excel to do that by just taking the formula here and calculate it here. And that number should be negative 1.94. So that's what we do by taking the sample and summarize it into one number, right? So negative 1.94 is about here, right? So if the null hypothesis is true, we should see this data and the sample with reasonable probability. And therefore, we would reject the null hypothesis if the probability of seeing that data is very small, right? So we would calculate what we call the p-value. The p-value is the probability of seeing the data or anything smaller. So basically it's the tail, right? And we look at the lower tail because of the fact that this is a lower tail test. So we calculate test statistics, we look at the lower tail and calculate the probability of seeing the data or beyond if the null hypothesis is true. And we would reject the null hypothesis if the probability is too small, but we see the data. So there's a contradiction. So how do we calculate the area from the test statistics and beyond? Well, basically that's the area or the probability of a standard normal distribution from this point all the way to negative infinity. So this is the tail area that we want to calculate. And to calculate that, we can actually use either a table. So we can actually go to a table, or we can use Excel to do that. If you go to a table, what we do is you go to negative 1.94, 1.94, you go to negative 1.9, go across to 4, and then you'll find that the probability is equal to 0.0262. Or you can actually use Excel to do it. If you use Excel to do it, the probability will be just norm.dist negative 1.94. And because it's standard normal, so mean is equal to 0, standard deviation is equal to 1, and this is a cumulative probability, so it's true. And so therefore, the p-value is 0.0262, which is the same as what we find from the table. So now that we calculate the test statistics and the p-value, then we can use the decision rule to make decisions. The decision rule on the rejection rule says that we will reject x0 if the p-value is less than 0.05. Well, is the p-value less than 0.05? Yes, 0.0262 is less than 0.15. So therefore, we can conclude that the null hypothesis is not true and the alternate hypothesis is true. So this is what we're going to write. You say we have sufficient evidence to conclude. And the conclusion is always about the research hypothesis that the mean cost is less than $26.6, right? Which is the alternative hypothesis there. So the conclusion is always about whether we would reject the null and consider XA is true, or we do not reject the null. Okay, so this is how we use the 5-step process to conduct a hypothesis testing problem. And the most important thing, of course, is when we use this approach because of the fact that the population standard deviation is given. Later on in another example, we see that the process would have to be changed if this is not the case. So let's use another approach to do the same problem. Another approach of doing the same problem is called the critical value approach. In the critical value approach, the decision rule is a little bit different. So the decision rule is, instead of comparing area, so in the last case, we calculate this, we compare this area, which is the p-value, with alpha, and see whether the area is less than alpha. In the critical value approach, instead of comparing the area, we're comparing points. We will compare the test statistics with a critical value that we found from the table. And obviously the idea is exactly the same, except that one is to compare areas, the other one is to compare points. So from that point of view, there's a number of steps that are the same. For example, the first step, setting hypothesis, would be the same. We would set the hypothesis the same way, right? HA is less than, and X0 is the opposite, which is bigger than or equal to. Alpha, of course, is the same. Alpha is equal to 0.05. So we do that. And now we have to do more work in the rejection rule because we have to find the critical value, right? So using the critical value approach, you have to find the minus Z alpha, right? So how do you find minus Z alpha? Well, if the area here is 0.05, what is the point that corresponds to the area equal to 0.05? Right? So the area, the point that corresponds to this area equal to 0.05 can be found by either using Excel, norm.inv, right? And the area is equal to 0.05, so it's 0.05. And then mean is 0, standard deviation is equal to 1, and that number is equal to negative 1.645. Or we can use the normal table, right? You can actually go and find the probability is equal to 0.05 and the number that corresponds to it, right? So the number is between 0.0505 and 0.0495, and therefore the point is negative 1.645. So either way, you will find the point that corresponds to area 0.05 is negative 1.645. And why we use looking at the area equal to 0.05? Because that's the level of significance. So now that we find this point, we will say reject x0 if the test statistics is less than negative 1.645. Okay? So you either would test the area, compare the area, or you compare the points. The approach is actually equivalent, as you can see. Now, so you do more work in setting up the rejection rule, but then you would do less work in terms of your test statistics. When you calculate test statistics, you go through the same step, and you list out what you know, and then you calculate the test statistic using the same formula as we have done. The calculation would give you negative 0.94, right? So where's negative 0.94? Well, this is negative 1.645. Negative 1.94 is here. So negative 1.94 is in the rejection region, and therefore we reject, right? So you say since Z equal to negative 1.94, which is less than negative 1.645. So therefore, we reject x0. So if we reject x0, what do we say? We say exactly the same as before, right? We say we have sufficient evidence to conclude. The mean cost is actually less than 26.6. So you either compare the area in the p-value approach, or you compare points in the critical value approach. And in both cases, as you can see, it's really helpful to draw a picture so that you would know exactly what you're dealing with. And drawing a picture is almost a must. It's much easier, as you can see, that we draw a picture so that we know exactly what we're doing. So this is the example that we have done using either the p-value approach or the critical value approach when the test is a lower tail test. So the next step for us is to show you how to do a hypothesis test when it's an upper tail test. So the next part of the example is this. We want to test the hypothesis that the population mean is more than 24.8 using a 0.05 level of significance. So this one is a upper tail test. Why? Because if you look at the HA is, as we always do, we write HA first. HA says the population mean is more than 24.8, right? So more than means upper tail. And so the opposite of HA is X0. X0 is the opposite of more than. So X0 would be mu is less than or equal to 24.8. Or if you really want to be lazy, you can just write mu is equal to 24.8. We will go through the same 5 steps. So it doesn't matter whether it's upper tail test, lower tail test, or two tail test, or any statistical test, you always follow the same 5 steps. Set the hypothesis, set the level of significance, set the rejection rule, calculate test statistics, and draw conclusions. So the second step in this problem is to set alpha, right? So alpha, again, we use alpha equal 0.05. So we're going to just, for the sake of doing it quickly, we can just copy and say alpha is equal 0.05 because that's what the answer, the question asks for. Now, the rejection rule. Again, we would do this problem with either the p-value approach, which we're going to do now, or the critical value approach, which we're going to do later. Under the p-value approach, how do we say it? We say reject x0 if the p-value is less than alpha. So p-value is preferred in most cases. Why? Because if regardless of what the test is, regardless of whether it's upper tail, lower tail, or two tail, the rejection rule is always the same. So you don't have to remember anything. Now, then the meat of the work would be in the test statistics and the calculation of the p-value. So let's do the test statistics first. Well, let's list out what we know, right? We know that x bar, of course, is equal to 25.5 because that's the data that we took, right? We know sigma is equal to 4 because that's given to us, right? Sigma is given to us. The sample mean is 25.5. The sample size, of course, is equal to 50, and then mu zero. Now, mu zero in this case is what? Mu zero in this case is 24.8, right? Because mu zero is the value that we want to test. So mu zero is equal to 24.8. So knowing this 4 quantity, all we have to do is to plug it into this formula again. So let's write this out. Z is equal to comparing what we see from the data, which is 25.5, minus what we want to test, which is 24.8, taking into account the availability, which is 4 divided by square root of 50. And we would be able to calculate that number. And again, I'm going to allow Excel to calculate it by just copy down formula here. And the number is equal to 1.12374. If you're using Excel, then you can just leave it as it is. If you're using the table, then you probably have to round up to 1.24 because the table only allows you to look at 2 decimal places. Now, this is where drawing a picture would be very helpful, right? So 1.24 is about here, right? So this is the normal distribution. Right? If you draw a standard normal distribution, and 1.24 is about here, right? And what is the p-value? The p-value is seeing this value and beyond. So we're looking at this area, right? So this is the area. If the null hypothesis is true, this is a standard normal distribution. And this is the probability of seeing what we see from the data if the null hypothesis is true, or the value beyond that. So that's the p-value, right? So what we want to do is to find either from the table or from Excel this area, right? This upper tail. Now, if you use the Excel function directly, Excel function only give you the lower tail. If you use the table is the same way. The table or Excel will only give you this area, but we want this area. So what we have to do is we have to do 1 minus that, right? So when we find the p-value, we do 1 minus norm dot dist, and the value is 1.2374, 0, 1, and 2. Now, there are programs that actually would calculate the p-value directly for you. You don't have to worry about this, but conceptually, you should be able to understand why is the case. And the way to do it is to make sure that you draw a picture and you will know, oh, this is the area, so therefore I have to do 1 minus, right? So basically what we says here, we know for a fact that the sample the sample mean is 25.5. Of course, 25.5 is bigger than 24.8. So we know that 25.5 is more than 24.8. The question is whether it's significantly more so that we can actually draw that conclusion, right? So we know that the number is going to be here, but is that big enough so that the probability of that happening is really small if the null hypothesis is true, and therefore we need to reject the null hypothesis. And that's the logic, okay? So now let me just calculate that number for you, right? So you would do 1 minus norm dot dist 1.2374 0 1 2, and that number is 0.108. So basically what we are saying is that yes, 25.5 is bigger than 24.8. Without statistical training, you would say, oh yeah, that the population mean is bigger than 24.8. But with statistical training, we say, okay, because of the variability that we have by taking a sample, there is 10% chance of seeing that value and beyond if the null hypothesis is true. And that probability is reasonable. And therefore, we cannot conclude that the mean is bigger than 24.8. If the null hypothesis is true, there's a 10% chance of seeing this value. All right, so let's just write it up. We say since the p-value is equal to what, 0.108, and you say, is that less than 0.05? It's not less than 0.05. We will reject the null if it's less than 0.05. We do not reject the null if it's not less than 0.05. So we do not reject x0. And if we do not reject x0, how do we write the conclusion? We say we have insufficient evidence to conclude. And what's the conclusion? The conclusion is always about xj, that the population mean is greater than, it's higher than, 24.8. Okay, so that's how you do this problem. For an upper tail test, this is how you go about doing it. Now, we can also use the critical value approach. In the critical value approach, of course, as we said, the null and alternate hypothesis is exactly the same if you use the critical value approach. The alpha is exactly the same, no different. And the difference is if you use the critical value approach, then the rejection rule is more, right? So the rejection rule says that we're going to reject the null hypothesis when the test statistic is too far away from 0 on the upper end, right? And how far is far enough away? Well, when the tail is 0.05. So we want to find this point so that the area corresponds to this point on the upper tail is 0.05. Now, we cannot find the value directly because of the fact that the table only gives us the lower tail. But then if we know the upper area is 0.05, the lower area is 0.95. So what we can do is to go to the table or using Excel to find the point that corresponds to this area equal to 0.95. So how do we do that? We go to the normal table and find a point that corresponds to 0.95, which is right here, which is right here, right? 0.9495 or 0.9405, which is 1.645. Or you can just use the Excel function, which is norm.inv.0.95, right? So by drawing the picture, you can see that if this is 0.05, this is 0.95, okay? So that you wouldn't make any mistakes. So 0, 1, 2. Sorry, that's it. We don't have to do 0, 1, 2. Okay, so as you can see, if we round it up to 4 decimal places, it's the same as what we have. It's 1.4645, and then now we can write the rejection rule. The rejection rule would be reject x0 if the test statistic is bigger than 1.645. Okay? And the calculation of test statistics, of course, is exactly the same. You don't have to do anything different. And you don't have to calculate the p-value because you're using the rejection rule, the critical value approach, right? So now we can make the decision. The decision should be the same, but we write it in a little bit differently. So we say since Z is 1.2374. Now, where's 1.2374? 1.2374 is here, and the critical value is here. The critical value is 1.645. This is 1.645, and our test statistic is here. So there's not in the critical region, and therefore we do not reject. Right? So we say since Z equal to 1.2374 is not greater than 1.645, right? Because in the rejection rule is that reject x0 if Z is bigger than 1.645. If it's not greater than, then you do not reject, right? So we say we do not reject. Oops, so I don't know what happened here. Since Z equal to 1.2374 is not greater than this, do not reject x0. And therefore, how do we draw the conclusion? We draw the conclusion exactly the same way. We have insufficient evidence to conclude that the population mean is higher than 24.7. Okay, so this is how we do a upper tail test using either the p-value approach or the critical value approach. The last step for this example, of course, to demonstrate what happens if we have a two-tail test. So the question would be like this. Test the hypothesis that the population mean is different from 24. So when you see the word different, you know that it's a two-tail test because the question says it doesn't matter if it's bigger than or less than as long as they are not the same. So either we see the word not the same or the word different. And so how do we go about doing it? Again, same 5-step hypothesis test. We set the hypothesis, we set the level of significance, we set the rejection rule, we calculate the test statistics, and we draw conclusion. And again, we can use either the p-value approach or the critical value approach. And as before, we're going to do the p-value approach first. Okay, so under the p-value approach, what is the first thing we do? We write out the alternate hypothesis. The alternate hypothesis is mu is not equal to, right? Not equal to. You can either write it in words or you can use it. You just say not equal to. It would be totally acceptable. And not equal to 25. And x8 then becomes, x0 become mu is equal to 25 because it's the opposite. Okay? So because of the fact that it could be bigger, it could be smaller because all your test is not equal to. So this is called a two-tail test. Okay, so two-tail test, that means that we have to consider either tail. Alpha, of course, alpha, as I said, you can actually just spell out the word alpha. Alpha in this case is 0.05, usually is 0.05, okay? And under the p-value approach, the good thing about the p-value approach is that the rejection rule is always the same. Reject x0 when the p-value is less than 0.05, right? So you can see that under the p-value approach, the rejection rule is always the same. Now, let's calculate the test statistic. Let's summarize what we know from the sample. What we know from the sample is x bar is equal to 25.5, right? 25.5. Sigma is given to us, which is equal to 4. N is known to us, which is equal to 50. And mu0 in this case is what we're trying to test. What we're trying to test in this case is 25. So mu0 is equal to 25. And now that we know the four numbers, all we have to do is to plug in to the test statistics and you find out, right? So the test statistic would be 25.5 minus 25, and taking into account the variability, which is 4 divided by s square root of 50. And let's do the calculation. And the calculation, just copy this. And the calculation will be equal to 0.8839. Okay. Now the challenge now becomes what is the p-value? Because of the fact that this is a two-tailed test, right? 0.8839 is here. So we can calculate this tail area, but because of the fact that this is two-tailed test, so how do we make it in two-tailed test? We take the small area, we go to the table, find the small area, and we multiply by 2. So take the probability, multiply by 2, will make this into a two-tailed test. So the p-value then is equal to, first of all, is 2 times the tail area, right? Because it's a two-tailed test. Sorry, two-tail is two-tail test. Okay, so but how do you calculate this area? Well, you calculate this area, so you theoretically you have to look at both sides, right? You have to look at this side and then look at this side. But because of the fact that normal is symmetric, so we can just calculate this area and multiply by 2. How do we calculate this area? Again, same before. We can take, because of the fact that the table gives us this area, right? So we can calculate this area, and 1 minus that would give us this area, and then we multiply by 2. Right, so let me just write this out for you. The p-value is equal to 2 times 1 minus the normal distribution and the lower tail for it, right? The lower tail is 0.8839, 0, 1, and 2. That's how you calculate the area. So 1 minus norm dist 0.0038, 0 and 2 would be this area. And then you do 1 minus to get this area. And then because of the fact that this is a two-tailed test, you multiply this area by 2. And so therefore, if you calculate this, then you should be able to get what you need. And that number is, let's see why we can't calculate this. That probability is equal to 0.37868, right? 0.37868. And again, is that bigger than 0.05 or less than 0.05? Because we reject x0 is the p-value is less than 0.05. And because of the fact that this is not less than, so we do not reject. So how do we write it? We say, since the p-value is equal to 0.3768, which is not less than 0.05, so do not reject. And I'm going to skip this one. I'm not going to write it out, right? So we'll say we have insufficient evidence to conclude that the mean is different from 25. Okay. Now, when we do if you do the critical value approach, and I'm going to go a little bit faster, the hypothesis would be exactly the same. Right? The hypothesis would be exactly the same using the critical value approach. Alpha would be exactly the same, equal to 0.05. And as before, because of the fact that you are using we're using the critical value, we find the two critical value. Now, here's what you need to pay attention. If this is a two-tailed test and alpha is equal to 0.05, we need to find 2 points because we don't know whether it's the upper tail or the lower tail. So we have to consider both upper tail or lower tail in a two-tailed test. And the total area is equal to 0.05. That means the area here as well as the area together is 0.05. So one side is equal to 0.025. So basically what we're looking for is, we're looking for a point so that the area here is 0.025, and we're looking at another point, the area is 0.025. But because of the fact that normal is symmetric, so all we have to do is find this point, and this point is going to be negative, and the positive side would give you the other point. Right? So now the problem of finding the critical value becomes finding the point so that the area here is 0.025. Okay, so how do we find the point here so that the area is equal to 0.025? You can either use the normal table, or you can just use the function norm inv 0.025 0 1 0 1, and that number is equal to negative 1.96. So if this is negative 1.96, this number would be positive 1.96. Right, so it should be around here, and it should be around here, and the critical value has two sides, right? So you can actually see that under the two-tailed test, using the critical value approach, Z is less than negative Z alpha over 2, or if Z is bigger than alpha over 2. So there's two sides to it. Z alpha over 2 is negative 1.96 and positive 1.96. So how do we write it? We say reject x0 if Z is bigger than 1.96 or Z is less than negative 1.96. Okay, so two sides because of the fact that this is a two-tailed test. And the test at T6 we already calculate, so we're not going to spend any more time doing that. So it's negative 1.8839, as you can see. And where is negative 0.8839? 0.8839 is actually here. So 0.839 is not in the rejection region, so we do not reject. Right? So how do we say it? We say since Z equal to 0.8839, which is not less than negative 1.96 or greater than, because you have two sides, right? 1.96. So they're not less than on this side, less than negative 1.96 or bigger than 1.96. So we do not reject. And do not reject, we will say we have insufficient evidence to conclude. Okay. So this is how you do the problem if it's a two-tailed test. So if you look back on what we have done, we actually have done all three scenarios: less than, more than, and different. And the formula for calculating the test statistic is the same, and the p-value approach is the same for the rejection region. You need to pay attention to how to find the p-value. For the critical value approach, you just make sure that you work on the critical value, and then you use the test statistics to calculate the value that you compare that with. So for population standard deviation is known, that's the value, that's the approach. So the next step for us is to look at hypothesis tests for population mean when the population standard deviation sigma is not known. How do you know the sigma is not known? Because it's not in the question, or you don't, in practice, you actually do not know. So let's get started on this one. So we say here in this example, on the left is a table of personal income tax refund of 35 people randomly selected in a research study. So there's no mention about the population standard deviation. So you know for a fact that all the techniques that we learned in the previous example is not applicable. You have to do something else. So here's the data. So what you have to do is to summarize that data, and then we use that data to do the hypothesis test. So for our first example, we have test the hypothesis that the population mean income tax refund is lower than $1,500 using a 0.05 level of significance. So what we need to do, obviously, because we want to test the mean, so the mean in this case, mu, is equal to the population mean income tax refund. Right? And what we need to do is to calculate from the sample mean, the sample standard deviation, and the sample size. So let's just do that, right? So the sample mean, of course, can be calculated from the data, and we use the average function, A2 to A36. Right, so that's how we calculate. Let me just put an equal sign in front of it, and it would be calculated. And if you take a look at it, and that is the data, right? So that's the average. And then the standard deviation can be calculated using the standard deviation function in Excel, which is equal to STDEV A2 to A36. And that number is $746.33. And sample size, of course, is 35, right? Because it says 35. And those are the basic quantities that we use in all calculation in the following. Now, let's look at the p-variables for this problem, right? So what we want to do in this problem is to test the hypothesis that the population mean is lower than 1,500. So lower means less than, right? So our XA is mu is less than 1,500. So this is a lower tail test. And HA then is, X0 then is the opposite. The opposite is mu is bigger than or equal to 1,500, or you can just like equal to, okay? So this is a lower tail test. And because we want to use the p-variable, so the rejection rule would be reject X0 if the p-value is less than alpha. Less than alpha, alpha is equal to, oh, sorry, I'm jumping the gun. Let me just finish this off. This is actually the first steps. Let me just cut it and put it over here. And what is alpha? Alpha is given to us, right? If we go at 0.05 level significance, so alpha is equal to 0.05, and alpha is always given to us. And in practice, for the most part, you use 0.05. All right, so now we have to calculate the test statistics. How do we calculate test statistics? Again, we compare what we see X bar with what we want to test with mu0, and taking into account the availability. But because of the fact that we do not know sigma, the population mean, so we use the sample population standard deviation. Then we use the sample standard deviation as a substitute, which is a typical approach in statistics. So instead of sigma over square root n, we have S over square root n. And because of that substitution, the distribution that we're going to use is a t distribution. And t distribution has a degree of freedom. So we need to, first of all, we need to recognize the fact that we cannot use the normal distribution anymore. And the second thing we need to recognize is that we need to calculate the degree of freedom. Okay, so let's write down what we know. What we know is X bar is equal to 1406.86. S equal to 7646.33. N is equal to 35. Oh, sorry, it's too close. And mu0, of course, is equal to mu0 is equal to 1,500. Okay, so now let's calculate test statistics. Test statistics is a statistics. Compare what you see, which is from the data, which is 1406.86, with what you want to test, which is 1,500, taking into account the availability, which is 746.33, divided by square root of the sample size, which is 35, and that number should be equal to a number that we calculate. And we can use Excel to calculate that if you want. Which is equal to negative 73.8 0.7383, right? So now, once we calculate test statistic, how do you find the p-value? Well, 0.7383 is here, right? And the logic is exactly the same. The p-value is the tail area, right? So how do we find the tail area? Unfortunately, we cannot really use the table. The t-table will look like this, right? The t-table only give you, for different degree of freedom, the area, right, in selected points. So the t-table is not useful. We can only do approximation. But if you really want to be accurate, you can always use Excel, right? So in Excel, we can use this function, right? We can use t dot dist, right? So equal sign t dot dist, right? And the point that we're looking for, negative 0.7383. And then we need to specify the degree of freedom. Now, the degree of freedom is always n minus 1. For this problem, the degree of freedom is n minus 1. So it's 35 minus 1. And then, of course, it's 2. Okay, so let me just write down the degree of freedom is, later on when we have other problem, the degree of freedom is not n minus 1. But in this case, it's n minus 1, which is equal to 35 minus 1, which is equal to 34. Okay, and so the p-value is, we can calculate by using this formula, t dot dist, bracket, the point, and the degree of freedom, and 2, right? And again, now that we have done this many times, we now know that we do not reject the null. Why? Because the p-value is not less than 0.05, right? So we say, since the p-value is not less than 0.05, not less than 0.05, so do not reject. Do not reject x0. And so we have insufficient evidence to conclude that the mean refund is less than 1,500. Now, if you're going to do the same problem using the critical weight approach, and since we have done it a few times, you're going to go a little bit faster. If you use the critical weight approach, your hypothesis would do exactly the same, and your alpha would be exactly the same, right? And so your decision rule is a little bit different because you're using the critical weight. So what we have to do is, from the t-table, or from the t-distribution, find a point that corresponds to an area that is equal to 0.05. Now, if you use the t-table, which you can at the back of your any textbook, you find the degree of freedom, which is 34 in this case, and you go across, and you can only see the point that corresponds to the table, the tail at the upper tail. And in this case, it's lower tail. But t is, as you can see from the graph, and you should always draw a graph, it's very much like normal, right? The t-distribution it looks like normal, right? So you can always find the negative and the positive, right? So you can actually just say, okay, I want an area at 0.05. I can go to the table, I find 0.05, and go down and find the degree of freedom, which is equal to 1.691. And then from here, we know that this number is negative 1.691. Or you can actually just do this. You can actually just do equal sign t dot inv. Let me just put down the degree of freedom first, right? So the degree of freedom, of course, is equal to n minus 1 is equal to 35 minus 1, which is equal to 34, okay? And therefore, the critical value is t dot inv. The tail area is 0.05 because alpha is equal to 0.05. Right, the degree of freedom is 34, and that's it. Right, and that number is negative 1.6909. So if you keep only 3 decimal places, it will be negative 1.691 as we found. Right, so we say reject x0 if t is less than negative 1.691. So you can see that the logic is exactly the same as before, except that we're using a different table. Instead of using the normal table, we use the t-table. and drawing a picture would always help you, right? And the calculation of test statistics, of course, is exactly the same, so we're going to keep that, right? And then we can draw the same conclusion. What is the conclusion? You compare, we don't really have to calculate the p-value. The test statistic is negative 0.738, right? So our rejection region is, if we will reject x0 is t is less than negative 1.691. So this is negative 1.691. And our test statistic is 0.738. 0.738 is here. So therefore, the test statistic is not in the rejection region. So therefore, we do not reject. So we say, since t is equal to negative 0.738, is not less than negative 1.691, so do not reject. So the logic is exactly the same for any critical variable, same thing. We use different problem, we use different table, and it's always helpful if you draw a picture on it. So our next step would be to see how we do a upper tail test if the population standard deviation is not known, okay? So here's an example. Test the hypothesis the population mean income tax refund is higher than $1,150. Okay, so how do we go about doing it? Well, we do it exactly the same way, right? So first we write down the alternate hypothesis. The alternate hypothesis is bigger than 1150, right? And if this is the alternate hypothesis, the null hypothesis would be, mu is less than or equal to 1150. And so therefore this is an upper tail test. If you use the p-value approach, alpha of course is always equal to 0.05. And if you use the p-value approach says reject x0. The p-value is less than alpha, and the test statistics, right? So how do we calculate test statistics? Compare what you see, which is 1406.86. This is the X bar with what you want to test. What you want to test is 1550, right? So this is 1550, comparing what you, right? And taking into account availability, so this is 746.33 divided by square root of 35. Okay, so using same formula, it doesn't matter if it's upper tail, lower tail, or two-tail test, compare what you see, x bar with mu0 divided by s over square root n, which is what we have. And I already have the calculation here. The calculation tells us that the number is 0.361. And so it's actually just right around here. And same logic before. We want to find this area, right? Because this is an upper tail test. How do we do that? We calculate the probability of this and 1 minus, right? So how do we do that? We do 1 minus, right? So let me just write that for you. You do 1 minus t dot dist, because this is a t distribution, right? 2.0361, right? And we calculate the degree of freedom. The degree of freedom is 34, and then 2. Right? So I actually should always write down the degree of freedom, right? The degree of freedom is equal to 35 minus 1, which is equal to 34. Okay, so this is the p-value. And so again, we can make decision if the p-value less than 0.05, yes, so we would reject. So we say since the p-value is equal to 0.0248, which is less than 0.05, yes. So we reject x0. Reject x0 means that we have sufficient evidence to conclude that the mean is bigger than 1150. Okay, so that's how you do it. We can do the critical failure approach. If you use the critical approach to do the same problem, the hypothesis test is exactly the same. Alpha is exactly the same. The rejection rule is different because you're using the critical approach. Right? The critical approach, if it's an upper tail test, is reject x0 if t is bigger than alpha. Right? So we need to find the area alpha here, 0.05, and we want to find the point that corresponds to 0.05. So how do we do that? We do that by using equal sign t dot inv. And it's our point, this is 0.05. So if this is 0.05, this area is 0.95. Right? So drawing a picture, you can see that you should use 0.95, degree of freedom is equal to 34, and that's it. And the number is 1.6909. Right? So we say reject x0 if the t distribution, the t statistic is bigger than 1.6909. And the calculation of test statistic would be exactly the same. So we've done that before. So let's just copy these down here. And so 2.03 is right around here. The critical value is 1.69. Our test statistic is here. So it's in the rejection region, so we will reject, right? So we say since t equal to 2.0361, this is greater than 1.6909, so we reject, right? Greater, we reject, so we reject, okay? So this is the upper tail test. Right? And the approach is exactly the same as before, right? So now you get a sense of how we do it in either the p-value approach or the critical value approach. So let's finish it off by looking at the third case where it's different, right? So different, in this example, we say test the hypothesis that the population mean income tax refund is different from $1,550. So let's write down the alternate hypothesis. The alternate hypothesis is they're not the same, so you can say it's different, not equal to. So English is okay. There's nothing wrong with spelling it out in English. Right? And then x0, of course, is mu is equal to 1550. And so this is not because of the fact that the alternate hypothesis is not equal to this is a two-tail test. Everything is the same except the calculation of the p-value as well as the critical value because of the fact that this is two-tail test. If you use the p-value approach, remember two-tail test, we multiply the tail by 2, right? So again, alpha, of course, is equal to 0.05. Right, rejection rule, right? So how do we do the rejection rule? We say reject x0 if the p-value is less than alpha, right? So the good thing about the p-value approach is it doesn't matter what the problem is, what tail, it's exactly the same. The test statistics, right? It's the same thing as before. Compare what you see, 1406.86. This is the sample mean versus what you want to see, what you want to test. You want to test against 1550 and taking into account the variability, which is 746.33. That's the sample standard deviation divided by square root of n. Square root of n is 35. And so that's the test statistics. And all you have to do is to calculate that. All right, so you should get really good at it now. And that number is, so something wrong. Let's get that negative 1346. Okay, so that's the test statistics. And how do we find the value? So let's draw a picture. This is a t distribution with the degree of freedom of don't forget the degree of freedom is 35 minus 1, which is equal to 34. So how do we do that? Well, negative 1.13 is actually here, right? And so we find this tail area, right? And because of the fact that this is a two-tail test, so we find this area and multiply by 2. How do we find this area? We just use the Excel function. So the p-value is equal to 2 times, right, t dot inv negative 1.1347, and the degree of freedom is 34. Okay, so the reason why we don't have to do 1 minus is because we are looking for this area. This area is exactly what the function gives us, so we don't have to do 1 minus. So by drawing the picture, you can actually see what is that you're trying to compute. Okay, so let me just copy this down and then just find out what the p-value is. Okay, something wrong here. So let me just fix it. So let's just do it again. So equal sign 2 times t dot inv, right, negative 1.1347, and then 34. And it should be okay. Something wrong here. I don't know what's wrong. Okay, so let's do it one more time, 2. So t dot inv. Okay, so h135. Let me just copy this one, and then the degree of freedom is 34. Okay, so let's just do that one. Oops. Oh, sorry. I'm obviously. So we should actually do 2 times dist, TDIST. Sorry, I'm getting a little bit tired, right? T dot dist negative 1.1347, and then 34, right? So that's why it's okay. So we should actually have, oh, I should actually spell true as well. Okay, so that's what we have. So the p-value is 0.2644. So we now can make decision. We say since the p-value is equal to 0.2644, this is obviously greater than 0.05. And if it's greater than, less than, we reject. Greater than, we do not reject. So we do not reject x0. Okay. So if you do the critical value approach for the two-sided test, obviously now we should be very good at it, right? The null hypothesis would be exactly the same. Your alpha would be exactly the same. How about the rejection rule, right? So because of the fact that this is a two-tailed test, the total area outside is 0.05. So one side is 0.025. So if you draw a picture, what we're looking for is we want to look for this point so that the area is 0.025. So how do we do that? Well, first we find the degree of freedom. The degree of freedom is 35 minus 1, which is equal to 34. And then the critical value would be equal to t dot inv, right? So this time. And then the probability is the tail area is 0.025. Because it's a two-tail test, 0.025, right? And then the degree of freedom is 34, and therefore the point that we're looking for is negative 2.0322. So our rejection rule would be reject x0 if t is bigger than 2.0322, right? Because T is symmetric. So if this is negative, it's right here, negative 2.0322, then the positive part is over there, would be positive 2.0322. So that's the positive part. Or you can also reject the null hypothesis if T is less than negative 2.0322. Okay, so that's how you go about doing that. Let me just copy this down a little bit more here so you can actually see. Right, now the test statistics, we've done it already, so we don't have to do it again. Right, so it's negative 1.14. So negative 1.14 is here. So if you draw a picture, you can see the negative 1.1347 is here. And it's not in the rejection region, so we do not reject. Right, so decision would be, since the T is equal to negative 1.1347, this is not less than negative 2.0322 or greater than 2.0322, so do not reject. Okay, so we look at all 6 cases when we have a hypothesis test for population mean and the population standard deviation is not known. This is a more realistic case because in practice, we do not know population standard deviation. And the last case, the last example I want to go through with you is the hypothesis test for population proportion. The logic is exactly the same. So I'm going to just look at 3 simple examples. We will show you how to use the formula, and we are now back to using the normal distribution. Okay, so here's an example. The proportion of female customers in a recent satisfaction survey of 500 listeners for a Toronto radio station is found to be 0.54, 54%. We want to test the hypothesis that the population proportion is greater than 0.5. And we want to use the p-value approach, and we want to use 0.05 level of significance. Okay, so because of the fact that we use the p-value approach, the p-value calculation is in order. So let's, just like before, you do the 5-step process. So it doesn't matter whether you choose the mean or you test for the proportion, or later on we're going to learn about how to do compare 2 samples and so on. It's always the 5-step process. So let's write down the alternate hypothesis. Let me actually, before I do that, let's define what the P is. The P is the population proportion of females. So that's what we're trying to make inference on, right? We want to see whether the proportion of females is bigger than 0.5, right? And so our alternate hypothesis is that P is greater than 0.5. Okay, so as we can say now, we know that this is a upper tail test, right? Because it's bigger than, and so the null hypothesis, sorry, is the opposite, which is P is less than or equal to, or if you want to be lazy, you can just write equal to. Okay, and this is obviously an upper tail test. We have done this many times now, so we probably are comfortable with it. The alpha, the level of significant alpha, of course, is 0.05, right? And the rejection rule, right? Because of the fact that we're using a p-value approach, they're always the same, right? So you can see, right? The rejection rule under the p-value approach is always reject x0 if the p-value is less than alpha and is true across the board, regardless of what the test is, right? So reject x0 is the p-value is less than alpha. So p-value is preferred because the rejection rule is always the same. Now the test statistic is a little bit complicated. Now because of the fact that we're testing for proportion, we now use again another formula, right? If you look at the formula, the setup is similar. You compare what you see from the sample, which is the p-bar. P-bar is the sample proportion, or the proportion from the sample. You can calculate from the sample, versus what you want to test. So you compare what you see with what you want to test, and then you divide by something. The something is the variability of P bar, right? So the square root of P0 times 1 minus P0 over N, okay? So let's write down what we know. P bar, of course, in this case is what you see from the data. What we see from the data, the proportion of female customers in this sample of 500 customers is 0.54. So P bar is equal to 0.54. And then N, of course, is the sample size, which is equal to 500. And P0 is what we want to test. P0 is what we want to test in the hypothesis, which is in this case 0.5. Okay? So now that we know the three number, we just have to get used to the calculation, right? So compare what we see, which is 0.54, with what we want to test, which is 0.5, and taking into account the variability, which is square root of 0.5. Now, the mistake is this is P0, not P bar, right? So P0 is 0.5. So P0 times 1 minus P0 divided by 500. And that's the formula. And so if you want to do the calculation, just copy down here, which is equal to 17889. Okay, so again, this is now we're back to normal distribution, and so this is 1.7889, and the p-value will be this upper tail, right? Because it's bigger than upper tail test. So we look at the upper tail as the p-value. So we want to find, we're given this point 1.7889, and we want to find this area. So how do we find this area? Well, we can either go to a table or using Excel, but either the table and Excel only give us this area, so we have to do 1 minus that, right? So the p-value is equal to, which is equal to 1 minus norm dot dist, right? 1.7889, mean 0, standard deviation equal to 1, and it's true. And the reason why it's 1 minus, because we're looking for the upper tail. The norm.dist give us the lower tail. The table give us the lower tail, so we do the 1 minus. And so the probability is, the p-value is 0.0368. And so now we can make decisions. If the p-value is less than alpha, we reject. If is this less than alpha? Yes. So this is less than alpha. So we reject. Now you can actually see the other thing about the p-value is that you can see how significant it is by looking at this number and compare with 0.05. If this is just less than 0.05, so in this case it's just less than 0.05. So it's, yeah, we reject, but the result is not particularly strong. If the p-value is equal to 0.00002, well, then the result is really strong. So by looking at the p-value, you actually can get a sense of not only whether you should reject x0, but how strong the result is. By the smaller the p-value, the stronger the result. So we say we have sufficient evidence to conclude. And what's the conclusion? The conclusion is always about the HA, right? So population proportion is greater than 0.5. Okay, so that's how you do it. And with the exception of the formula, everything is actually the same as before. And in this case, you're back to the normal table. Let's do a couple more examples. Test the hypothesis the population proportion is different from 0.51 using the p-value approach and the 0.05 level significance. So again, what is the alternative hypothesis? Alternative hypothesis is P is different. Different is not equal to. I don't even want to use the notation because I don't have time. And x0 would be that P is equal to 0.51. Right. So this is a two-tailed test because it's not equal to alpha. Again, alpha is equal to 0.05. p-value opposed, so we say reject x0 if the p-value is less than 0.05. Right? The good thing about the p-value approach. And then the calculation of test statistics, let's write down what we know. P bar is equal to 0.54, right? P bar is equal to 0.54, right? And n is equal to 500. P0 is, in this case, P0 is equal to 0.51. Okay, P0 is 0.51, right? 0.51 is the hypothesis. So what is Z? Z is equal to, let me just write down Z here. Right? Compare what you see, which is 0.54, and what you're trying to test, which is 0.51, taking into account the variability, which is square root of 0.51 times bracket 1 minus 0.51 divided by 500, and that number is 1.3419, right? So 1.3419 is around here, and this is a two-tail test. So what do we have to do? We have to find the upper tail, and then we multiply by 2. So how do we find upper tail? Find this area, right? Because this is what's given to us. 1 minus that, and then multiply by 2, right? So if you draw a picture, you can actually see easily, right? So p-value is equal to 2 times, let's just do that, right? 2 times bracket 1 minus, again, we're back to normal, right? So normal distribution, and 1.3419, 0, 1, 2. By the way, obviously, we can use another function. We can use norm.s.dist, and then you don't have to do 0 and 1, but it doesn't matter, right? So the p-value is 0.1796. So now we compare this value with alpha. If it's less than 0.05, we reject. Is that less than 0.05? No. So we do not reject. So we say since the p-value is equal to 0.1796, this is not less than 0.05. So do not reject. And reject, we say sufficient evidence. Do not reject, we say we have insufficient evidence, right? So if we do not reject, you say insufficient evidence. Conclude, and the conclusion is always about the alternate hypothesis. The population proportion is different from 0.51. Okay, so this is always about the exchange. Okay, so this is how you do the two-sided test for proportion. This is our very last example. Our last example says use alpha equal 0.05 and the critical value approach to test whether the population proportion is less than 0.59. Okay, so we should be really comfortable now. The first thing we do is to write down the alternate hypothesis. Less than is 0.59. And if it is less than, then HA is equal to 0.59 or bigger than or equal to, same thing as we keep saying. Alpha is equal to 0.05. And now this one is a critical value approach. So let's draw a picture. We want to find this point so that the area, because it's lower tail, the area is 0.05. So we want to find a point that corresponds to 0.05 tail area. So how do we do that? We do norm.inv, right, 0.05, because this is 0.05, and you find the value, so you don't have to do anything. 0, 1. That's it, and that number should be negative 1.645. So we say reject x0 if Z, which is the test statistic, is less than negative 1.645. All right, so now let's calculate the test statistics. So how do we do that? All right, compare what you see from the data. The data says 54%, And what we're trying to test, is 0.59, 0.59, and taking into account the variability, which is the square root of 0.59 times bracket 1 minus 0.59 divided by 500 at negative 2.273, right? So the common mistake, as I said, is if this is P0, the bottom is also P0, not P bar, okay? And so now we can make decision, right? So where is negative 2.273? If you draw a picture, you can see the negative 2.273 is here, and this is negative 1.645. So negative 2.273 is less than 1.645. It's in the rejection region. So what do? We reject, right? So we say since Z is equal to negative 2.273, which is less than negative 1.645. And because the fact that it's less than, so we reject x0. And reject x0 means that we have sufficient evidence to conclude that the proportion is actually less than 0.59. So that concludes the 3 examples that I want to share with you today. And I know that it's really long, but I hope that the whole process is comprehensive enough so that you get a complete picture of how to do hypothesis testing using either the p-value approach or the critical value approach. And you also get an appreciation of how to deal with the situations in upper tail test, lower tail test, or two-tail test. So I hope that you enjoyed this long video, and I hope to see you next time. Bye for now.